energy. Let's take a look at this this figure right here. I want to erase a couple of things before we really get going with that. Okay, let's take a look at this figure right here. Potential energy can really be described here with this kid with the rubber band. Not the rubber band, but with a slingshot. If you stretch a slingshot, you're doing work. You may remember that work is defined by motion. We had a guy in a previous video that was up against a wall, pushing the wall. He couldn't get the wall to move. He wasn't really doing any work, even though he probably sweated up a storm if he kept pushing on it for a long time. But work is defined by actual movement. So when you're doing a slingshot like this, you're actually transferring energy. You're transferring energy, first of all, from you, the boy in this case, to the rubber band. So we have an energy transfer from the boy to the rubber band, and then when he lets go, the energy will then be transferred from the rubber band to the rock or the stone that happens to be there. So when work is done, energy is transferred or transformed. And one way to define energy is that energy is the ability to do work. Energy is the ability to do work. Now we're going to have a couple of different terms of energy on this video, and there's another one coming up on the next video. One term, potential energy, is where you really don't have any work that's being done yet. But if you notice this little kid right here, I mean, it's obvious to see that all he has to do is to release that slingshot, and there's work being done, because work is defined by motion. There's going to be a lot of motion once he releases it, because that ball or stone's going to travel however far. So we'll have energy, we'll have work once he does that. But in the meantime, while he hasn't done that, he has a lot of potential energy. This slingshot has potential energy. The rubber band has potential energy. The stone has the potential energy. The bowler with the bowling ball has potential energy. All these are energies of position. Energy of position is called potential energy. I guess I can do that a little bit better with my pen here. Energy of position. So depending on where something is, it will have more or less potential energy. If that rock the kid has in that slingshot, well, if it's on the ground, it doesn't have much potential energy at all. But if it's in a slingshot ready to go, it will have a lot of potential energy. Now, kind of like this ball that's on the top of the hill here. This ball is just balancing right there. It has a lot of potential energy. Sure, it probably won't be too long before it goes down one side or goes down the other and does actual energy, energy of motion. But for right now, it contains, scientists would say it contains energy just from its position. And that will bring us to this apple right here. This apple has potential energy. Why? Because the apple is just hanging there. And if the apple were to be severed or were to fall from the tree, which it probably would at some point, then it will have movement down to the ground. It will have movement down to the ground because of gravity. So you can say, even though the apple just sitting there, probably sat there, well, it has sat there all its existence, has potential energy that it will fall one day. And that kind of potential energy we're going to define as gravitational positional energy. Now, we can't really do much defining of much measuring until we actually get some motion. So potential energy is a little bit less defined as the actual energy turns out to be. I'm looking at my notes to see if I have moved anything around, and I think I'm in pretty good shape here. So we're going to actually define gravitational potential energy right here. Now, gravitational potential energy is going to be mass times the free fall acceleration of gravity times the height. So if we were doing the apple, it'd be the mass of the apple, gravitational acceleration, and the height. Now, the gravitational acceleration has been determined on Earth at regular levels to be 9.8 meters per second squared. That's something that will be in every equation if you're on Earth. You actually have different calculations for other planets because you have different gravities there. But who's going to calculate an apple falling on a different planet? So let's see about units here. Mass is going to be calculated in kilograms. If you happen to be at grams, you have to convert it over to kilograms. Gravitational free fall is going to be at meters per second squared. Hey, did you notice? If you multiplied kilograms times meters per second squared, you get newtons. That's what we did with force equals mass times acceleration, which is kind of the first part of this. The force is the mass times the gravitational acceleration, and we did that one in newtons. Now, whenever you have newtons and you multiply it times height, height is going to be in meters, so you have Newton meters, which equals to joules. So gravitational potential energy is going to be written in joules, just like work was written in joules. So we're going to calculate a few of these things. Let's take an apple. Now, I'm just taking stabs at the kilogram mass of apple, because you know we kind of measure in pounds a little bit more than we do in kilograms. So gravitational potential energy equals to mass times gravitational free fall times height. So gravitational potential energy, let's fill in the numbers, equals the mass, looks like it is 0.2. I'll just put 0.2. The gravitational free fall is 9.8, just right above here, as we have mentioned before. And the height, let's see, looks like it is 2 meters. So all we have to do is multiply these together. We'll go to the handy dandy dashboard, and we'll multiply 0.2 times 9.8 times 2 equals 3.92 joules. Is going to be the answer. 3.92 joules. Okay, let's go to another one. We'll go with red on this one. Looks like we have a car. So the GPE, gravitational potential energy, is. Now keep in mind, these are things that are falling. These are things that are falling. We have an apple that's falling from a tree. We have a car. Well, let's have the car go over the cliff. The cliff is going to be 80 meters high. The car is going to weigh 1,200 kilograms. So these are all calculations for things that are falling. So we have 1,200 kilograms multiplied times 9.8 meters per second squared, multiplied times, looks like about 80. So it will be 80 meters. So what do we have? 12, I better clear it. 1,200 times 9.8 times 80. 940,800. So the GPE equals 940,800 what? It'd be joules. Because here you had kilograms times meters per second times meter. Meters per second squared times meters. Let's go to a different color for the marble. This marble, you can see the height is very high. Chose to have if a marble were falling out of an airplane. So I wonder how it would compare in the joules to a car falling. Car is falling, but it's only at 80 meters. The marble is falling out of an airplane at a huge height. So let's find out. GPE equals, the marble is 30 grams, nowhere near the size of the car. multiply it times the free fall, gravitational free fall, which is going to be 9.8 meters per second squared. Multiply that times 4.5, oh, scientific notation, times 10 to the third power. Now what I'm going to do, I'm going to multiply just times the 4.5, and then I'm going to end up adding the zeros after that. That's something you can do. So let's go to the dashboard. 30 is the grams, kilograms, times, ooh, you know, I just noticed. That's in grams. So we're going to have to convert that to kilograms. So 1 kilogram equals 1,000 grams. So if you have 1 kilogram equals 1,000 grams, then that means that is 0.003, is that right? 1, 2, 3, no, it's not. So it'd be 0.030. Yeah, 0.030. So instead of multiplying by 30, it would be multiplying times 0.03. See how that goes. I'll change that. So let's go down here. We have 0.03 times 9.8 times 4.5. Now keep in mind we're going to have to add those 3 zeros at the end. 1.323. 1.323. Now since we have times 10 to the third, we had to move the decimal over 3 places, which looks pretty darn easy from here. Got this decimal 1, 2, 3. So that made it easy for us. The gravitational potential energy is 1,323 what? Joules. So how did it compare to the gravitational energy of this car? It was nowhere near the gravitational energy of this car. The car had far, far, far more joules or more gravitational potential energy just because it weighs so much more. But it did have more potential energy than this apple. The apple weighed more than it did. It was just 0.2 instead of being 0.03. But the height of it is what ended up tipping the scales for that one.